pick up here a variety of places, but basically we're going to talk now about, since last time I believe we finished types of reactions and how to classify them. We're going to kind of put together a couple of those things. We're going to put together grams and moles and obviously balancing equations. And we're going to talk about stoichiometry in this chapter, just these lectures here. We'll talk about basic stoichiometry problems. We'll talk about limiting reagent type stoichiometry problems. We'll also talk about percent yield. And then we'll transition into a little bit of talk about solutions and concentration for solutions like molarity. And we'll kind of finish up there, I think, talking about sort of titrations, which is a big experiment coming up, I think, towards the end of next week, if I'm not mistaken, the big experiment of the season. All right, so first off, we're going to talk about stoichiometry, and stoichiometry is really using the balanced equation as sort of conversion factors. So, for example, if we had an equation such as this, we would obviously want to make sure that we balance it like normal here. And from a balanced equation such as this one here, we basically look at the coefficients, and they basically can sort of describe several different types of relationships. You could go through the coefficients and say, for example, that there would be one molecule of N2 reacts with 3 molecules of H2, and that gives you 2 molecules of NH3. The more sort of useful relationship, and the relationship that we use the most here, is the sort of mole to mole relationship. We could also go through and say for every 1 mole of N2, it reacts with 3 moles of H2, and that produces 2 moles of NH3. So in stoichiometry, we really use this sort of multiple relationship, and really the purpose of sort of stoichiometry is a lot of times you're given information about somebody in the reaction that you're not necessarily interested in, and you want to find out about maybe another reactant, or maybe you want to find out about another product that's in the reaction. So you really need a way to go from, a reactant to product, product to reactant, between reactants or between products. And there's not like a table you could go in the book and sort of look up the conversion factors. So where we get the conversion factors are just from the actual balanced equation. So always in stoichiometry, and anytime you're dealing with an equation, you got to always make sure it's balanced. Otherwise, it really will throw everything else off. So from this particular equation here, we could have several different relationships. We could say for every 1 mole of N2, we also need to put in there 3 moles of H2. We could say for every 1 mole of N2 we put in there, we get 2 moles of NH3 out. And we could also say for every 3 moles of H2, we get out 2 moles of NH3. These are what are referred to as being stoichiometrically equal to each other. They are clearly not equal to each other in terms of numbers, because I still believe 3 doesn't equal 2, but maybe some places it does. But basically, they're equal to each other sort of as proportion-wise what you need to throw into that reaction, basically for it to sort of come out correctly. So kind of like when you make cookies, right? You need so much flour, so much chocolate chips and butter and all that kind of stuff for to get a dozen cookies out. You need the right proportion of all these sort of reactants to produce a certain amount of products. So these are referred to as being stoichiometrically equal to each other. They're really equivalent to each other, which means they're equalities. And from each of these equalities, you really could write 2 conversion factors. You could write, for example, 1 mole of N2 over 3 moles of H2, or 3 moles of H2 over 1 mole of N2. From this guy, you could write 1 mole of N2 over 2 moles of NH3. are 2 moles of NH3 over 1 mole of N2. And lastly here, we could write something like 3 moles of H2 over 2 moles of NH3 are 2 moles of NH3 gives us 3 moles of H2. So really from this one sort of balanced equation, we have really 6 different conversion factors that we could use in a problem. Obviously, you probably would only use one, most likely, out of all those, but obviously you would choose whichever one would work correctly for you. So again, for example, if I said I produced 6 moles of NH3, how many moles of N2 did I start with? We can basically do just a simple dimensional analysis conversion. We would start with our 6 moles of NH3. We would go to our equation and find the 2 things we're interested in. So obviously that is one thing we're interested in. That is one thing we're interested in. And that gives us this equality, which gives us these 2 conversion factors that we could use. And in this case, we would just do dimensional analysis. So we want NH3 to cancel. So we would use the first conversion factor here to do so. And that would get us 1 mole of N2, 2 moles of NH3. So here the NH3 moles will cancel. I'll try it without the calculator. I believe that's a 3. Moles of N2 was actually started in this reaction, obviously taking 6 divided by 2. If I want to know how many grams that would be, I could do one more conversion, right? Take it from moles to grams, and I could use the molar mass of N2. And that would be 2 times 1401 grams per mole of N2. And that would roughly give me about 80 something there. I didn't hit times again. Let's try that again. There we go. Getting about try that again. You know, you're getting old when you got to bring the calculator this close. All right, 84, about 84 grams there of N2. So these are sort of the basic steps for a stoichiometry problem. You do have to sort of get things into moles first, so you can use the mole-to-mole relationship within the equation. So oftentimes up front, you're also using molar mass to kind of go from grams to moles. Use the mole-to-mole relationship there from the equation. And a lot of times you don't really want the answer in moles, so you have to convert to some other unit. Obviously here we did grams, which is a very common unit at the end. Sometimes you may be asked for any unit, you can pounds or something like that. So you may do more conversions there towards the end. Any questions on that? Yeah. Yeah, so really in this question here, we were only really given information about NH3, right, in this reaction. But we're actually not interested in NH3. We're actually interested, again, in this case of N2. So that's where we have to use, really, this is the big stoichiometry move right there. We have to use the equation to basically find a conversion factor. I mean, for the most part, that's pretty much what stoichiometry is. It's just a conversion factor. And instead of, again, looking up in a table, you get it from the balance equation is pretty much what it is. People like to make it all big and crazy, but it's basically just a conversion factor that you get from the actual equation. And we do that because in a lot of these problems, like I said, we're sort of given information about somebody else in the reaction, but we want to relate it back to, you know, maybe another reactant or product. When we do stoichiometry, you do not have to cross over the arrow. So what I mean by that is, you know, you could do stoichiometry between the 2 reactants. If you had an extra product on this side, you could do it between the 2 products. You could also, obviously, like we did here, go across the arrow that way or that way. So sometimes people think you always kind of have to cross over the arrow to do some type of stoichiometry. You don't. You can see on the left-hand side of the arrow and do it between the reactants. You can do it between the products, or you could go obviously between reactants and products. In a basic stoichiometry problem, which is pretty much like this one here, and it's pretty much any question where you're just given basically one piece of information about anything in the question and the reaction. There's really just 4 basic steps that you follow, and these are pretty much the 4 basic steps, no matter how crazy the reaction may look, how crazy the numbers may look. If it is just a basic stoichiometry problem, you basically just follow these steps. First off, it all starts with a balanced equation. So in a lot of cases, you are given the equation, but you definitely should take a look at it and make sure it's balanced. If you see some numbers, it probably is balanced. If you do not see numbers, then I would definitely take a really hard look at it to make sure it's balanced. If you're given everything in words, then you definitely want to make sure that you convert everything into the proper formulas first and then balance the equation. Pretty much, if you do not start with a balanced equation, you're screwed for the whole entire rest of the calculation there. So it's got to be balanced. The next thing that you want to do is take whatever units they give you and you want to get them into moles. So most commonly in these type of problems, you're going to be given grams and you're going to need to go to moles. And once again, that is the molar mass from the periodic table that allows us to do that conversion. Once you have it in moles, step 3 is really the stoichiometry part. You go to the equation, you find the 2 things you're interested in, and basically you find the mole to mole relationship, which is going to give you your conversion factor that you need to use. Lastly, if you do everything correctly, you should definitely be in moles at this point. You may have to do step number 4, and that would be the moles into some other unit. So if they happen to want the answer in moles, you just put a box on it. But if they do not want the answer in moles, you may have to do 1 conversion, 2 conversions. Again, very common on the back end of these calculations. You're going from moles to grams. And once again, that molar mass is going to be sort of your conversion factor on the back end. Any questions on that there? All right, so we're going to try one here. Just make one up and see how we do. We'll go with C3H8 plus a little O2 action, some CO2, and some water. So if we started with, let's do 42.5 grams of C3H8, how many grams of CO2 would be produced? All right, so take a couple minutes. I'm going to give you some numbers that might be helpful here. Carbon is 12.01, hydrogen 1.008, oxygen 16. I think that's everybody, I think. Okay, let's take a look and, okay, hold on. Let's take a look and see how we're doing. So again, this is what would be considered sort of a basic stoichiometry problem. Again, we're really only given one piece of information about C3H8. We're interested though in CO2. So that again tells you it is a stoichiometry problem. So the basic 4 steps is we need an equation that is balanced. And in this case, it is not balanced. So that is definitely where you want to start. So to balance this guy up, a little 3 action there, a little 4 action there, and maybe like a 5 action there, I hope. That should then be balanced, I hope, at that point. Any questions on that? All right, so that was like step number 1, balance pretty much the equation. Again, do not go past go if you do not do that. Step number 2 is basically take whatever they gave us and we're going to convert it into moles. And in this particular case, we are given grams, which means we do need to do that. In order to do that, we do need to go to the periodic table and we need to get the molar mass of this guy. And that would then be for our C3H8, 3 times 12.01 for our carbon. plus 8 times 1.008 for our hydrogen. Thank you. And that gives us 3 times 12.01 plus 8 times 1.08. And I believe it's 4409 would be the molar mass there. That is grams per mole, which again, we're going to use as a conversion factor. So we'll take the numbers that were given to us, 42.5 grams, C3H8, little dimensional analysis action, which we all like. So 4409 grams per mole, C3H8. Grams here will cancel, and 42.5 divided by 4409. Going to get us, we'll call it 0.9639. And these are still moles of C3H8. All we really did is just change the units. Any questions up to that point? The reason we need to do this step and get it into moles is really for the next step, which is the stoichiometry part. So in this case, for step number 3, we're going to do the mole to mole relationship. So we will go to our balanced equation there and find the 2 things we're interested in. Obviously, one thing we're interested in is what they gave us. The other thing we're interested in is what we're trying to find, which is the CO2 in this case. And we're going to take the coefficients. Pretty much that's all you do. And that tells us from the equation, for every 1 mole of C3, bless you, H8, you get 3 moles of CO2. Remember, from that equality, you could get 2 conversion factors, 1 mole C3H8 over 3 moles of CO2, or 3 moles of CO2 gives you 1 mole of C3H8. So using that stoichiometry from the balanced equation, we're going to take our answer here, which is 0.9639 moles. We're going to do the big stoichiometry move. To get rid of the C3H8, it needs to go on the bottom, which means that is the conversion factor we need to use. So we're going to do 3 moles of CO2 up on top, 1 mole C3H8 on the bottom. Those 2 guys will cancel. We're going to multiply it by 3, and we will get something like 2.8918 moles of CO2. Any questions up to there? That is close to what we need. If we did want moles, we would be done. Obviously, we could put a box on it, but we are looking for grams. So we do need to do step number 4 here. And at this point, step number 4 is going to take the moles, in this case, to grams. We do need to, though, get the molar mass here of CO2 at this point and not use the same molar mass as above. So that would be 12.01 for our carbon, plus 2 times 16 for our oxygens there. Going to give us a little 4401 action there for our molar mass of CO2. So using that to finish this up here, 2.8918 moles of CO2, 4401 grams up on top. So we end up with grams, moles of CO2 on the bottom so that they cancel. Gets us about 127, maybe it says. 127 grams of CO2. Any questions on any of those steps there? Can you do it all in one calculation? Absolutely. Yeah. So, but I just broke it up so you can see the 4 steps. If you want to do it individually like this, you can. You can put it all together. If you do it individually like this, try not to round to the very end. Yeah. So just keep the number, kind of keep going with it to the very end. But either way, or you can just put all the steps together there. Any questions on any part of that? Pretty much every basic stoichiometry problem, those 4 steps. Yeah. Just do the steps in order. If something is done for you, just go to the next step. Don't undo it. I've seen people do that, like, oh, it's in moles. Let me unconvert it and reconvert it back to moles. So don't do any of those things. I always try one more here, which I think is the one you got on your book there. Little methanol burns in air, has the following equation. Methanol is the CH3OH. So we're looking for how much water is going to be produced in this case. And once again, same numbers basically as before, 1201 for carbon, hydrogen 1.008, and oxygen 16. This is a basic stoichiometry problem. I do know that because I'm pretty much just given information about this guy. I eventually want to get all the way over there to the water. So basically our pathway, right, is to balance the equation, which it is. We're going to take our grams to moles or mole to mole relationship. And then obviously in this case, our moles back to grams on the back end of it. So in this case, step number one, pretty much done for us. It's balanced, so that's good. We would then proceed to converting what they gave us into moles. So using the molar mass from the periodic table, we got 12.01 plus 4 times 1.008 for all of the hydrogens and a 16, I believe. That gets you 3204 grams per mole for our CH3OH. So using that as our conversion factor here, we want to get rid of grams. So we're going to put the grams on the bottom, which will be 32.04 grams per mole of CH3OH. At this point, the grams of CH3OH cancel. We again want to go from the methanol in this case to the water. So the next step would be the mole to mole relationship. And again, from the equation, we can see for every 2 moles of CH3OH, we get 4 moles of water. So continuing on with our calculation here, our moles of methanol are up on top. So to get rid of them, we go opposite. So they'll be on the bottom. And our moles of water will go up on top. At this point, if we stop the calculation, our moles of methanol cancel, and we are in moles of water, which again is close to what we want, but we do want grams. So the last thing here is obviously to get the molar mass of water from the periodic table. Plus 16. Going to give us 18.02 grams per mole. And setting this up, in this case, we want the moles to cancel. So the moles of water will go on the bottom. The 18.02 grams will go up on top. Moles cancel. We're going to multiply across the top there, 209 times 4 times 18.02, and then divide by on the bottom, 3204, and divide by 2. Looks like we get 235 grams of water was produced in this case. This is also sometimes referred to as the theoretical yield in this case, which is how much you should get in this reaction. Basically, what that number represents is if you dump 209 grams of methanol into this reaction, everything went perfect, no side reactions, you weren't a klutz and spilled everything on the floor. You should get about 235 grams of water out in this reaction. Is your maximum amount of product that you should get based on the equation. In this case, obviously, I put all the steps together, but again, you could do it individually as well. It is still the same basic 4 steps. That is step number 1, step number 2, step number 3, and step number 4. Any questions on basic stoichiometry problem? Okay. So the next thing we're going to talk about then is actually limiting reagents. And whenever a reaction basically takes place, both reactants, for example, don't always react evenly. And there's always a reactant that pretty much gets used up first in the reaction. And that's what's known as the limiting reagent, or limiting reactant is sometimes called, is the one that gets used up first in the reaction. Now, there's usually a reactant or a reagent that you have plenty of, which is referred to as the excess reagent, and that you have plenty of. And you usually have some of this left over at the end of the reaction. So, for example, the reason why limiting reagents are really important is, for example, if you took A plus B to make the classic A-B combination. And if A was my limiting reagent, and at some point it gets used up, there pretty much is no hope of ever making the product here, right? Because you need an A and you need a B, and if A is gone, there is no more product. So the limiting reagent is always the one that determines how much product you can produce. So the limiting reagent is always the one that determines how much product you produce. Right. So like they used to, I think they still do, right? Sell you hot dogs and hot dog buns, like eight hot dog buns and 10 hot dogs, or the other way around, right? You're always short, right? You always run out. I'm sure it's just coincidence. That's how come they do that. But so obviously you'd be limited by the hot dog buns there to get complete hot dogs. So same idea here. Always a limiting reagent that determines it. So when you have a limiting reagent problem or limiting reagent sort of situation, the way you can pretty much recognize it is you are given enough information about both of the reactants to get the moles. So if you look at it and you have enough information for both reactants to get the moles, it's a limiting reagent problem. So if you have enough info to get to moles for all reactants, it definitely is a limiting reagent problem here. So if you think about the couple of problems we just did, we pretty much were only given one piece of information and one piece of information about a reactant. And in those type of problems, it's assumed that whatever information they give you, if it is a reactant, that's the limiting reagent, and the other one is the excess reagent. So that's why you don't have to figure it out in those kind of basic stoichiometry problems. But if you are given enough information for both of those, you will need to sort of figure out which one's the limiting reagent. The good news is there are a few different ways you could do it. You could do the same 4 steps. It's just somewhere in between there. You got to figure out the limiting reagent before you continue on with the final part of the calculation. You also can, in these type of problems, also figure out how much of the excess reagents left over. So those are very common type of questions. You know, how much are you going to produce of products? How much of that excess reagent is left over? So let us go through one here together that I'm going to make up. We'll go with this equation because I saw it earlier and I feel like I could still balance it. Maybe. There we go. So let's say we started with, we'll do 10 grams of H2 and 45 grams of N2 were reacted. How many grams of NH3 will you produce? All right, I just made that up, so we'll go with it. All right, so I'm going to show you one way first, kind of a classic way, if you will, semi-classic, old, one of those things, way of doing it. And then I'm going to show you a different way, which can be a little bit more beneficial to you, and I'll explain why when we get there. By the way, there are multiple ways that you could do limiting reagent problems. So if you learned a way earlier on there last semester in the earlier class and you still like it, go with it. I don't really care as long as it's a legitimate way of doing it. But I'm just going to show you a couple of different ways. And like I said, you could kind of choose whichever way you think you like the best. All right, so first off, we know it's a stoichiometry problem. The second thing here is I see I have 10 grams of H2. I got 45 grams of N2. That means that without a doubt, I could get to moles of each of those reactants. So right off the bat, that tells me that this is a limiting reagent problem, which again means somewhere along the way, you gotta figure out the limiting reagent. Pretty much no matter what path you choose, what sort of way you do these problems, they're all pretty much the same. Got to balance the equation still. You still got to convert what they give you into moles. So that's what we're going to do here. I'm going to convert each of those into moles. So we'll take our 10 grams of H2 and we'll take our 45 grams of N2 and we'll do a little conversion into moles here. So 2 times 1.008 grams per mole. And 2 times 1401 grams per mole. That comes from obviously the periodic table here. So 10 divided by gets me 4.960 moles of H2. That gives me 1.606 moles of N2. So these two numbers basically represent the starting amount of both of our reactants. So one approach to a let's figure out the limiting reagent type problem is you take one of your reactants that you're starting with, and you basically do a small little calculation to figure out how much of the other reactant you would need to put in there. So that's what I'm going to do here. It doesn't matter which one you choose. I'm going to choose H2. And what I'm going to do here is take the moles of the H2. And I'm going to use the stoichiometry from the equation between H2 and N2, which is 3 moles of H2 gives me 1 mole of N2. Moles of H2 cancel, and that gives me 1.65 moles of N2 in this case. Okay. So what this represents is how many moles of N2 is needed. Clearly should have picked some better numbers, but we'll go with it anyways. So this is basically how many moles of N2 is needed. And what we want to then do is compare to our starting amount. And in this case, do we have enough moles of N2? I need 1.65 moles of N2. I have 1.61 moles, fairly close on my bad number choice here, but I think that is not enough. Yeah. So because that is not enough, that means that this is our limiting reagent, the N2, and the H2 by default would be our excess reagent. So that is one way you can determine which one is the limiting reagent. A very bad number choice. So once I do that, I now know that in this case, the N2 is our limiting reagent. So what we're going to do is now do the actual rest of the calculation. I'm going to pick up part 3 and then part 4 of the calculation. We're now going to use our limiting reagent, which is N2, to figure out how much product we're going to make. And that's always what we want to use here. So we'll go with 1.606 moles of N2. We do want to use this starting amount here in our calculation. So this calculation was just to figure out, which was the limiting reagent. We're going to now do the stoichiometry between N2, which is 1 mole, and NH3, which is 2 moles of NH3. That gives me about 3.212. And of NH3. We then can figure out how many grams that is by using the molar mass of NH3 from the periodic table, which would be like step number 4. And the molar mass here of NH3 is 1703 grams per mole. And that would then tell us that we should produce here approximately 54.7 grams of NH3 in this case. So that is sort of one approach that you could do when you are doing these type of problems. Another very common approach, and probably taught most of the time, is you just do 2 separate stoichiometry calculations, one from one reactant to the product, one from the other reactant to the product, and whichever one gives you the smallest number of product is the limiting reagent and your theoretical yield. So that's a very commonly taught one. Probably most people taught that way. Yeah. So that is very commonly taught, is just to do 2 separate ones, and whichever one gets you to gets you to the smallest number of product would be it. So this is, again, another approach. You also could use this to figure out how much of the excess reagent that you would need to use. So in this particular case, if we wanted to, we would have to go back and do another calculation to figure out how much of the excess reagent is left over. So in this particular case, we would need to sort of do the opposite calculation. We would have to take, I know that this guy right here is my limiting reagent. Now to figure out how many moles of my excess reagent I would need to use, we would do our 1 mole of N2 to 3 moles of H2. And that would be 4.818 moles of H2 was used in this reaction. And we started with 4.96. So we would have to subtract those 2 numbers. And that gives us, well, I really chose pretty close numbers here, huh? 4.818. That means that we have left over 0.142 moles of H2 in this reaction, which we could times by 2.016, approximately 0.28 grams of it left over. I almost used it all up, just made up numbers. So in this sort of approach, which perfectly works, you could just choose any of the reactants to figure out the limiting reagent. Once you figure out the limiting reagent, you start with the starting amount of limiting reagent to figure out how much product you make. Then you do have to come back and kind of do a separate calculation to figure out how much of the excess reagent is left over. Any questions on that approach there? All right, so I'm going to show you how to do this problem a different way, and limiting reagent problems a different way than maybe you've learned before. And the benefit of the way I'm going to kind of show you, if you give it a chance, is you could very, very quickly figure out every answer to any question that they ask you pretty quickly. Within a couple of moves, you'll have pretty much every answer you may be asked, like how much of all the products, how much of the leftover is left over. The additional benefit of what I'm going to show you is pretty much the main calculation in 200B. So you'll have a preview of the main calculation you do in 200B, which might help you there as well. All right, any questions though on this approach here? All right, so we're just going to do the same one, and what I'll do is pick up here. Put all those there, I think. All right. So starting with the same problem, again, like I said, no matter what approach you take, pretty much you got to convert those guys into moles to begin with. So we'll just keep that there. All right. The next thing we're going to do here is the second approach, and it's what is referred to commonly as an ice table. So this ice table approach, which like I said, is pretty much the main calculation you do all day in 1B or 200B, is the ice table approach. And in our application here, ice stands for initial, C stands for change, and E stands for end. When you get to 200B, E stands for equilibrium, but it's kind of the same idea here. So to do an ice table, like I said, you do pretty much the exact same two steps. You're going to take your balanced equation. You're going to convert everybody into moles, and that's going to be what goes on your initial line in the table. So initially, we had for N2, 1.606 moles. For H2, we had 4.96 moles. And we had 0 here for NH3. Any questions on that part so far? Now, the next part, which is the change part, is really the most important part here. This is where we take into account the stoichiometry, the multimole relationship. So we represent usually in ice tables the change as like X. So X is kind of like the guy we represent as like sort of like an unknown. And we do take the coefficients into account. As this reaction is happening and we go from reactants to products, is the amount of reactants increasing or decreasing? Reactants are, to make products, you need reactants, yeah? And reactants then should be decreasing, yeah? It's the only way to make products. We'll do our hot dog example. If I needed to make a hot dog, I got to take a hot dog, put it in a bun, put it on the side, less hot dogs, yes? So same idea here. Reactants should be decreasing with time. Products should be increasing with time. So we represent that in an ice table as reactants are minuses and products are pluses, like they're gaining and subtracting. So here on the change, we go minus X, and again, X is the change. We go minus 3X, and the 3 is because of the coefficient. And if you do not put the 3, you have the wrong multimole relationship. We didn't put a number on the first one because number here is 1, yeah? So 1X basically is X. Over here, this should now be our products that's increasing plus 2X, yes, on this side. Once again, the 2 for the coefficients. That is equivalent to the 1 mole to 3 mole to 2 mole relationship that we did earlier in the stoichiometry part. Any questions on that there? All right, so at the end here of our ice table, we're just going to bring everything down. So 1.606 minus X, I'm going to get the moles out of there so it doesn't get too crowded. 4.960 minus 3X, and this is 2X. All right, so this is the part in the table where we could determine which one is the limiting reagent. And we're going to do that by setting each of the reactants equal to 0 and solving for X. So we're going to set this guy equal to 0, which means all I do is move the X to the other side, right? And X in this case would equal 1.606 moles. I'm going to set this guy equal to 0, which means 3X, moving that to the other side, equals 4.960. And that basically means 4.960 divided by 3, 1.653. So again, I just kind of quickly set them equal to 0, solve for X. A lot of times you have one like that where it's just basically the same number. Any questions on that part? Now, whichever X value is the smallest would be your limiting reagent. So in this case, which one's the smallest? It is the nitrogen, yeah? So that is the smallest. And that would mean that is your limiting reagent. And by default, once again, that would be your excess reagent. Now, once we determine that, we really don't need this calculation anymore. Again, it was just to help us determine which one is the limiting reagent. Now, why this is important is that is our X value in our table, which is that X value. It is that X value. and it is that X value, which means really quickly I could determine pretty much anything that I need. So for example, we wanted NH3. NH3 from the N line is equal to 2 times X, which means it is equal to 2 times our moles there, 1.606, which gets us our 2 times 1.606, 3.212. Of NH3, which we could then obviously multiply by our molar mass of our 1703, right? Getting us 54.7, I think. The benefit of this is if I wanted my excess reagent, which is this guy, I can see from the table that my excess reagent is equal to 4.960 minus 3 times X. And this will tell me that 4.960 minus 3 times our 1.606 moles will tell us that we have left over what we saw there a second ago, hopefully. Looks like 0.142 moles, I think. And timesing that by 2.016. Gets us 0.286 grams of H2 left over. And clearly, if I put it into here, it would equal pretty much 0, right? Because that's the limiting reagent, should be all used up. The benefit of this as well is if you had another product over here, you would have another end line there that you could quickly figure out how much of the other product was produced as well. So this sort of calculation can be really helpful and kind of quick to get you to all those very common questions. Like I said, how much product you produce, how much is left over, the excess reagent. Any questions on that approach? Yeah. You could do any way you want as long as it's a legitimate approach. So again, this one is very helpful, could get you to a lot of answers really quick. Also will help you if you're going on to 200B. That's pretty much a calculation you do all day. Yeah. Yeah. You would not. So in this case, for example, if there was something else there, you would have carried down, you would have started with a 0. It would have carried down to something X basically. And you would just put your X value into that, and that will give you the moles of the second product. Yeah. Other questions on that? All right. So why don't you try one then here? In one process, 124 grams of aluminum are reacted with 601 grams of iron 3 oxide. How much aluminum oxide is produced? So aluminum is 698, oxygen is 16, and iron is 5585. Okay, let's take a look. So once again, we are given 124 grams of aluminum. We got 601 grams of our iron 3 oxide. So that definitely is enough information to get the moles for both of our reactants. So again, that's how we do know that this is a limiting reagent problem, and you should approach it that way. Again, no matter which way you go with it, you got to have a balanced equation, which it does look like we have. You also need to convert those guys into moles. So that's where I'm going to start here. So I'm going to take the 124 grams of aluminum. I'm going to divide by the molar mass from the periodic table. And that will give me for aluminum 124 divided by 2698. Looks like a 4.596 of aluminum. We're also going to convert our 601 grams of iron 3 oxide into moles, and molar mass of that would be 2 times 5585 plus 3 times 16. Looks like 159.7 grams per mole. So 159.7, so 601 divided by 159.7, get me 3.763. All right. Any questions up to there? All right, so I'm going to do the ice table again to show you it so you can see it again, in case you like it. All right, so remember here, initially, we're just going to put our moles in there. So our aluminum is 4.596 moles. Our iron 3 oxide is 3.763 moles. And again, it is safe to zero out initially everybody on the product side. Once again, we're going to lower our reactants, increase our products. So minus is on the left, plus is on the right. We also, again, need to take into account the coefficients as we do this part. So that's going to be minus 2x. That will be minus x. That will be plus x and plus 2x here. That means when we get to the end here, tearing down our numbers, 4.596 minus 2x, 3.763 minus x, x and 2x. Any questions on the table here? This again is where we're going to basically determine which one is the limiting reagent by solving for x and setting each of the reactants equal to 0. So 4.596 minus 2x equals 0. Move the x to the other side and divide by 2 gives you an x value of, basically divide by 2.298. Remember that this value is in moles, is basically what it is. This guy we're going to set equal to 0, which means we do get basically the same number. So x here will equal 3.763. Once again, we want the smallest number, which is this guy. Which means it is our limiting reagent. We do not need this anymore. So that means out of this reaction here, it is the aluminum that's our limiting reagent. By default, it means our excess reagent would be the iron 3 oxide in this case. Any questions on that there? All right, so let's answer the question that was asked first off here, which is how much aluminum oxide? And we can see at the end here, the moles of aluminum oxide equals X, which in this case is 2.298 moles of aluminum oxide. We could use the molar mass of aluminum oxide to convert that into grams. So that is 2 times 2698 plus 3 times 16 at 102 grams per mole. So 2.298 moles of aluminum oxide and 102 grams per mole is the molar mass from the periodic table. That will get us 2.298, about 234 grams of aluminum oxide would be produced here. And that would be the theoretical yield here of aluminum oxide. Any questions on that? Now, again, the benefit of doing this is it wasn't asked in this particular problem, but if we want to know how many grams of iron we would produce, what should we do? iron would equal 2x, right? So the moles of iron in this case would equal 2 times x, which means 2 times 2.298 moles, which means we would also produce 2 times 2.298, 4.596 moles of iron, which if we want to know how many grams that would be, we could use the molar mass of iron, which is 5585. And that would be 257 grams of iron was produced. So again, without having necessarily to back up from the very beginning, we could really quickly figure that out. And the last thing that you're oftentimes asked is how much of the excess reagent is left over. So we could go back there to that, and our excess, which in this example was the iron 3 oxide, would equal 3.76 moles minus our X, 2.298. Means that we have 3.763 minus 2.298, 1.465 moles of iron 3 oxide left over, which we do have the molar mass right there. So we can multiply that by 159.7 grams per mole. And we got about actually 234 grams of the iron 3 oxide left over. So we started with 601 grams of the iron 3 oxide. We have about 234 of it left over. We used 300 and some change there in the reaction. So as you can see, it didn't take very long to pretty much answer any question that you might be asked using this approach. And again, sort of the benefit of it is that you don't have to use it if you don't like it. But if you want to use something else, you should get the same numbers. Yeah. Any questions on any parts of that there? So I would say in our approach here, you would want to use the ice table only in a limiting reagent situation is really where it'd be beneficial. In a regular basic stoichiometry problem like we did at the beginning, just doing the 4 steps is really probably the quickest way to do it. But this is really beneficial in a sort of a limiting reagent sort of situation. But if it is a limiting reagent situation, pretty much you could just do this for any situation that's that. But I would recommend, again, in a basic one, just do a regular stoichiometry sort of calculation. It's better, yeah. Because you, in a basic stoichiometry one, you already know the limiting reagent, so you don't have to really